Most galaxies are measured in tens of thousands of light years. This one is measured in millions. There exists a single galaxy so large that, if it replaced the Milky Way, our entire local group of galaxies would simply vanish inside it. Not over time. Instantly. In terms of scale, tonight, we're going to trace how a structure this extreme can form, how it keeps itself together, and why its existence quietly reshapes what we think a galaxy actually is. When you hear the word galaxy, you probably think you already know what it means. A vast collection of stars, a spiral shape floating in darkness, something enormous, but still, in some sense, familiar. After all, we live inside one. We've seen images of galaxies our entire lives. They appear in textbooks, documentaries, phone wallpapers, even logos. The idea feels settled. But the problem is not that this idea is wrong. The problem is that it's incomplete in a way that quietly misleads almost everything we think about scale. At its simplest, a galaxy is a gravitationally bound system made of stars, gas, dust, and a large amount of something we cannot see directly: dark matter. Gravity is the glue that holds all of this together. Without it, stars would drift apart into intergalactic space, and galaxies would dissolve over cosmic time. In that sense, a galaxy is not defined by shape or beauty, but by gravity. If enough mass is bound together strongly enough to resist the expansion of the universe locally, we call it a galaxy. That sounds straightforward, but already, something subtle is hiding inside that definition. Gravity does not stop abruptly. It does not create walls. It fades with distance. And because of that, galaxies do not have clean edges the way most objects we are familiar with do. A city has a border. A country has a line on a map. Even a forest has a place where trees noticeably thin out. A galaxy does not end in that way. It slowly, gradually dissolves into emptiness. As you move outward from the center of a galaxy, the density of stars decreases. There are fewer stars per cubic light year, then fewer still, until eventually the average distance between stars becomes so large that the region blends into what we call intergalactic space. But there is no moment where you can point and say, "This is where the galaxy stops." There is no cosmic fence, no sharp cutoff, just a fading presence. This immediately creates a problem. If galaxies do not have edges, how do we measure their size? When astronomers say a galaxy is 100,000 light years across, what exactly are they measuring? Are they measuring where most of the stars are, where the light drops below a certain threshold, where the dark matter halo effectively ends? The answer depends on context, and this matters far more than it might seem right now. To make this concrete, imagine standing in the middle of a foggy field at night with a flashlight. Close to you, the light is bright and obvious. As you move farther away, it becomes dimmer and more diffuse. At some distance, the light is still there, but it's faint enough that you stop noticing it. Did the light end, or did your ability to see it end? Galaxies behave in a very similar way. Much of their mass and structure lies in regions that are extremely faint, difficult to detect, and easy to ignore if you are not looking carefully. This is why two astronomers can measure the same galaxy and give you two very different sizes without either of them being wrong. One might measure the bright inner region where most of the stars are concentrated. Another might include the faint outer halo that extends far beyond what is easily visible. Both measurements describe the same object, just with different definitions of what counts as part of it. And here is where our intuition really starts to fail us. Most of the mass of a galaxy does not come from the stars we see. It comes from dark matter. This invisible component forms a vast halo surrounding the galaxy, extending far beyond the visible stars. We know it is there because of its gravitational effects. Stars orbit faster than they should. If only visible matter were present. Gas clouds move as if something massive is pulling on them. Galaxies within clusters behave as though they are embedded in enormous, invisible structures. All of this points to dark matter halos that can be several times larger than the visible galaxy itself. So, when you picture a galaxy as a neat spiral or a smooth ellipse floating in space, you are really seeing only the bright core of something much larger and more diffuse. You are seeing the tip of a gravitational iceberg, and that mental image, while useful, quietly trains you to underestimate just how large galaxies can actually become. Another common misconception is that galaxies are isolated objects, like islands separated by vast oceans of empty space. In reality, galaxies exist within a cosmic web, a network of filaments made of dark matter and gas stretching across the universe. Galaxies form along these filaments, grow by pulling material from them, and interact with other galaxies that share the same gravitational environment. In dense regions, galaxies collide, merge, and tear each other apart. In quieter regions, they evolve more slowly. Environment matters. This means that a galaxy is not just the result of its own internal processes. It is the product of its surroundings, its history, and the gravitational landscape it inhabits. Some galaxies remain relatively modest in size because they live in isolation. Others, placed in crowded cosmic neighborhoods, grow through repeated mergers, absorbing smaller galaxies over billions of years. The difference between an average galaxy and an extreme one is often not how it started, but where it spent its life. So when we ask, what is a galaxy? The most honest answer is not a simple definition. A galaxy is a gravitational process stretched out over billions of years. It is a structure without a clear boundary, shaped as much by what it consumes as by what it contains. It is not a static object, but a dynamic system, constantly changing, constantly interacting with its environment. This matters because the galaxy we are about to talk about does not just stretch the upper end of what we think a galaxy can be. It exposes how misleading our everyday mental model has been all along. If you assume galaxies have neat edges, fixed sizes, and simple shapes, then something like IC 1101 sounds almost absurd. But once you understand that galaxies fade rather than end, that they grow through mergers, and that their true extent is often hidden in faint halos and invisible matter, the question shifts. The question is no longer how could a galaxy become that large? The question becomes, under the right conditions, why wouldn't it? And with that in mind, before we look at IC 1101 itself, we need to ground our sense of scale in something familiar, because the galaxy we live in already feels unimaginably vast. And yet, by cosmic standards, it is only the beginning. It is one thing to say that galaxies are vast in the abstract. It is another thing entirely to live inside one. Perspective matters. And nothing shapes our intuition more strongly than the fact that the Milky Way is not something we observe from the outside, but something we inhabit from within. When you are surrounded on all sides by something, it tends to feel endless, even when it is not. The Milky Way contains somewhere between 200 and 400 billion stars. Even the lower end of that estimate is difficult to hold in your mind. 200 billion is not just a big number. It is a number that stops behaving like a number at all. If you tried to count one star per second, without ever sleeping, without ever stopping, it would take you more than 6,000 years just to reach 200 billion. At the upper estimate, closer to 400 billion stars. The counting would take over 12,000 years. Writing itself is only about 5,000 years old. You could have started counting stars when the first humans carved symbols into clay, and you would still not be finished today. And yet, astronomically speaking, the Milky Way is considered a fairly average galaxy. Not especially small, not especially large, just typical. That realization alone took humanity a long time to accept. For much of our history, it was natural to assume that the galaxy we lived in must be special. It is enormous by human standards. So why wouldn't it be exceptional by cosmic ones? But the universe has a way of humbling that kind of assumption. In terms of physical size, the Milky Way stretches roughly 100,000 light-years from one side to the other. A light-year is the distance light travels in 1 year. About 9,46 trillion kilometers, or roughly 5,88 trillion miles. Multiply that by 100,000. And you get a number so large that writing it out feels almost pointless. It is easier to approach the idea indirectly. Light is the fastest thing in the universe. Nothing with mass can move faster. And even at that ultimate speed, light takes 100,000 years to cross our galaxy. 100,000 years. That means the light leaving stars on one side of the Milky Way began its journey toward the opposite side before modern humans existed. Before agriculture, before cities, before language as we know it, the galaxy we live in is so large that the fastest thing in nature requires a time span longer than all of recorded human history just to traverse it. If that still feels abstract, imagine trying to cross the Milky Way by car. Suppose you could drive at highway speed, about 60 miles per hour, without stopping, 24 hours a day, every day of the year. No sleep, no fuel stops, no breakdowns. At that pace, crossing our galaxy would take over 1 trillion years. The universe itself is only about 13.8 billion years old. You would need to drive for roughly 80 times the entire age of the universe just to make it across one fairly typical galaxy. Numbers like this stretch the limits of human intuition. We did not evolve to think in terms of trillions or hundreds of thousands of years. Our brains are tuned to distances we can walk, drive, or perhaps fly across, and to timescales measured in days, years, or lifetimes. When numbers grow too large, they lose their emotional weight. They become symbols rather than experiences. This is why astronomers rely so heavily on analogy, even knowing that every analogy will eventually fail. From our position inside the Milky Way, the galaxy feels like everything. The stars we see in the night sky are overwhelmingly members of our own galaxy. The faint band of light stretching across the sky on a dark night. The Milky Way itself is the combined glow of billions of distant stars, too faint to resolve individually. It wraps around us, enclosing us in a luminous disk of starlight. It is hard not to feel that this structure must be enormous beyond comparison. But this feeling is, in a sense, a trick of perspective. Living inside a structure makes it feel larger than it would if you could step back and see it whole. A forest feels endless when you are standing among the trees. A city feels boundless when you are navigating its streets. Only when you view them from above do their limits become clear. We do not have that vantage point for the Milky Way in any direct sense. We reconstruct its shape and size from indirect measurements, mapping star positions, motions, and distributions, building a picture piece by piece. And when we do that, something surprising emerges. Our galaxy, as vast as it feels, is not extreme. It sits comfortably in the middle of the distribution. There are smaller galaxies, many of them, dwarf galaxies with only a few billion stars or even fewer. But there are also galaxies that are much larger, containing trillions of stars and extending far beyond the scale of the Milky Way. We tend not to think about them because they are distant, faint, and difficult to study, but they exist nonetheless. Another reason the Milky Way feels especially large is that it is structured in a way that emphasizes scale. It is a spiral galaxy with a disk that extends far outward, making its diameter impressive. But diameter is only one way to think about size. Mass, number of stars, total gravitational influence, and the extent of the surrounding dark matter halo all tell slightly different stories. A galaxy with a smaller visible disk but a massive halo can exert influence over a much larger region of space than its appearance would suggest. This distinction matters because when we talk about extreme galaxies, we are often not just talking about brighter spirals with longer arms. We are talking about systems whose true size lies mostly in regions that are faint, diffuse, and easy to overlook. Regions where stars are sparse, but gravity still holds sway. Regions that extend far beyond what casual observation would ever reveal. So the Milky Way serves as both a useful reference point and a dangerous one. It gives us a sense of what a galaxy can be. But it also anchors our intuition too tightly. It makes us think in terms of 100,000 light-years as a kind of upper limit, when in reality, that number is just a starting point. Once you accept that our galaxy is merely average, the idea of something dramatically larger stops being unthinkable and starts being inevitable. If there are billions of galaxies, all forming under different conditions, over billions of years, why would they all end up roughly the same size? Why would gravity, mergers, and cosmic environment conspire to produce uniformity rather than extremes? The Milky Way feels enormous because it is enormous, relative to us, but relative to the full range of structures the universe allows. It is only one data point among many, and when we finally place it alongside galaxies that occupy the far end of that range, the sense of scale shifts again. There is a moment in many areas of science where increasing a quantity stops adding clarity and starts removing it. Add more distance, more mass, more time, and eventually the numbers stop helping your intuition. They pile up without creating a clearer picture. In astronomy, that moment often arrives when we move beyond the scale of our own galaxy. For much of the early 20th century, astronomers did not even know how large galaxies could become. The Milky Way itself was still being mapped. The idea that galaxies came in radically different sizes had not yet fully taken hold. Most known galaxies appeared roughly comparable in scale, at least within the limits of the telescopes available at the time. Extreme objects tend to hide when your instruments are blunt. That began to change as telescopes improved and as astronomers started surveying not just individual galaxies, but entire clusters of them. One of the key realizations that emerged in the mid-20th century was that environment matters enormously. Galaxies living alone tend to remain modest. Galaxies living in crowded regions, surrounded by thousands of neighbors, do not. This was not a theoretical insight at first. It was an observational one. Astronomers studying rich galaxy clusters noticed that the brightest galaxy in the cluster was often not just slightly brighter than the rest, but overwhelmingly dominant. These galaxies sat near the gravitational center of the cluster and appeared unusually large, unusually diffuse, and unusually massive. They did not look like scaled-up versions of spiral galaxies. They looked like something else entirely. By the 1,960 seconds and 1,970 seconds, this pattern became hard to ignore. Studies of clusters, such as Coma and Abell-class clusters, revealed galaxies with extended halos of stars that stretched far beyond what had previously been considered normal. In some cases, these halos overlapped with one another, blurring the distinction between individual galaxies and the cluster itself. The line between a very large galaxy and the core of a galaxy cluster began to feel uncomfortably thin. This is where the language starts to struggle. We use the word bigger as if it were a simple extension of smaller scales. A bigger house, a bigger city, a bigger planet. But galaxies do not grow by being uniformly scaled up. They grow by collision, absorption, and redistribution. Their outer regions are not denser versions of their cores. They are tenuous, ancient, and shaped by countless past interactions. When astronomers measure the size of such a galaxy, the result depends almost entirely on what they choose to include. If you measure only the bright central region, you get one answer. If you trace the faint outer light down to extremely low surface brightness levels, the size can increase by factors of 10 or more. And if you include the full extent of the gravitational influence, including dark matter, the concept of a single size becomes almost arbitrary. This realization became sharper with the rise of deep imaging surveys. Long-exposure photographs taken with large telescopes began to reveal faint stellar envelopes around massive galaxies, envelopes that had been invisible in earlier observations. These halos were not small features. In some cases, they extended hundreds of thousands of light-years from the galaxy's center. These stars were not arranged in neat disks or arms. They formed a diffuse cloud, the fossil record of ancient mergers. At the same time, simulations of galaxy formation began to mature. With the advent of large-scale cosmological simulations in the late 20th and early 21st centuries, astronomers could model how galaxies grow over billions of years within a universe dominated by dark matter. These simulations consistently produced a population of extreme galaxies at the centers of massive clusters. They grew not because they formed unusually large at birth, but because they had privileged access to material. Gravity, in these environments, acts like a funnel. Smaller galaxies lose energy through interactions and gradually sink toward the cluster center, where they are absorbed by the dominant galaxy. This process, known as dynamical friction, is slow but relentless. Over billions of years, the central galaxy becomes a collector of stars, dark matter, and the stripped remnants of its neighbors. What is striking is not just that this happens, but how far it can go. There is no obvious hard limit imposed by physics that says a galaxy must stop growing at a certain size. As long as material is available and the gravitational environment allows it, growth can continue. The universe does not enforce moderation. This is the point where our earlier reference point, the Milky Way, quietly loses its authority. 100,000 light-years no longer feels like a natural scale. It feels like an accident of our location, a consequence of where we happen to form, not a rule of nature. Imagine trying to describe the size of oceans to a species that evolved in isolated lakes. You could explain that some bodies of water stretch beyond the horizon, that waves travel for days without hitting land, that depths exist where light never reaches. But until that species encounters the ocean directly, its intuition would resist the idea. Lakes feel large when lakes are all you know. Galaxies behave in much the same way. Once you accept that there are environments where galaxies can grow by consuming dozens or even hundreds of others, the existence of extreme outliers becomes less surprising. The surprising part is that we expected uniformity in the first place. This is where the story of IC 1101 begins to sharpen, even before we name it. Because IC 1101 does not simply sit at the upper end of a smooth distribution. It occupies a region of parameter space where familiar comparisons stop working. Comparing it to the Milky Way is like comparing a continent to a city. Comparing it to Andromeda, itself a large galaxy, does not restore intuition. It only emphasizes how inadequate our categories have become. And this has consequences beyond simple astonishment. When a single galaxy grows large enough, it begins to influence not just its own structure, but the behavior of the entire cluster around it. Gas flows differently. Orbits change. Even the evolution of neighboring galaxies is affected. At that scale, a galaxy is no longer just a member of a system. It becomes part of the system's architecture. So when astronomers realized that objects like IC 1101 existed, the shock was not merely about size. It was about what size meant. It forced a re-evaluation of how galaxies form, how they interact with their environment, and how we define the boundaries of cosmic structures. The word largest stops functioning as a simple superlative here. It stops meaning the same thing, but more. Instead, it signals a transition into a different regime, one where our mental models must change if they are to remain useful at all. And now that we have reached that threshold, it is time to look directly at the galaxy that pushed us across it, not as an abstract extreme, but as a real object with a location, a history, and measurable properties. Because once you place IC 1101 into context, the true scale of the universe begins to feel very different indeed. At some point, numbers alone stop working. Saying that a galaxy is millions of light years across sounds impressive, but it doesn't really tell you what that means. To understand the scale of IC 1101, you have to do something slightly uncomfortable. You have to take the structure you live inside, the Milky Way, and imagine removing it. Not moving it, not shrinking it, removing it entirely, and putting something else in its place. Picture the center of the Milky Way, the region around Sagittarius A*, the supermassive black hole that anchors our galaxy. Now, imagine that. Instead of our galaxy, the core of IC 1101 occupies that same point in space. Everything else stays where it is. The Sun, the Earth, the Orion Arm, all of it remains fixed. Only the galaxy itself changes. The first thing you would notice is not violence or chaos. On human timescales, nothing dramatic would happen at all. Stars are separated by vast distances. Galaxies, even when they overlap, are mostly empty space. But in terms of scale, the difference would be immediate and absolute. The Milky Way is about 100,000 light-years across. Ik omir suta unu, depending on how you measure it, spans somewhere between 4 and 6 million light-years. That means its radius alone is comparable to the distance between us and the Andromeda galaxy. Andromeda, our nearest large galactic neighbor, lies about 5 million light-years away. It already feels unimaginably distant. Light leaving Andromeda tonight began its journey when early human ancestors were just beginning to walk upright in Africa. In the IC 1101 scenario, Andromeda would no longer be a neighboring galaxy. It would be inside the same galaxy, not near the edge, not brushing against it, fully embedded within the outer regions of IC 1101's stellar halo. The faint spiral smudge that we see in long-exposure photographs would cease to be a separate object at all. Its stars would simply become part of a much larger structure, orbiting within a shared gravitational system. And IC 1101 would not stop there. The Triangulum galaxy, another significant member of our local group, sits roughly 3 million light-years away from the Milky Way. Under normal circumstances, it is a distinct island of stars, smaller than Andromeda, but still substantial in its own right. In this thought experiment, it too would be absorbed, its identity erased not by collision, but by scale. It would not be destroyed so much as reclassified by gravity. Even the galaxies that feel close to us, the large and small Magellanic Clouds, would barely register. These dwarf galaxies orbit the Milky Way at distances of roughly 160, 0, 0, 0, and 200, 0, 0, 0 light-years. In the context of IC 1101, those distances are trivial. They would sit deep within its inner regions, indistinguishable from countless other stellar groupings. When astronomers talk about our local group of galaxies, they are referring to a collection of more than 50 known galaxies bound together by gravity. This group spans roughly 10 million light-years from end to end. It includes the Milky Way, Andromeda, Triangulum, and dozens of smaller companions. It is our cosmic neighborhood, the largest structure most people ever hear about in detail. And a single galaxy, Ikomiyosuta Unu, is more than half that size. This is the moment where intuition usually breaks. A galaxy larger than a group of galaxies feels like a contradiction. After all, aren't groups made of galaxies? How can one object rival the scale of an entire collection? But the universe does not organize itself according to human categories. It organizes itself according to gravity. IC 1101 sits near the center of a massive galaxy cluster. Over billions of years, it has absorbed the remnants of many smaller galaxies, building up an enormous, to diffuse halo of stars. These stars did not form together in one place. They were captured, stripped, and redistributed through countless gravitational interactions. The result is not a tidy structure, but a vast, fading envelope that extends far beyond the bright core. From a distance, this envelope is difficult to see. Its surface brightness is extremely low, but dynamically, it matters. These stars are bound. They orbit the same gravitational center. They are part of the same system. This is why IC 1101 forces us to rethink what it means to say that something is a galaxy. If you focus only on the bright inner regions, the comparison with the Milky Way feels dramatic but manageable. But once you include the full stellar halo, the true extent becomes impossible to ignore. There is also an important observational lesson hiding here. For much of the 20th century, astronomers underestimated the sizes of the largest galaxies simply because they could not see their faint outskirts. It was only with deep imaging and careful analysis that these extended halos became apparent. In other words, IC 1101 did not suddenly become large. We gradually became better at noticing how large it already was. Studies in the late 20th and early 21st centuries, particularly those using wide-field imaging and long exposure times, revealed that many central cluster galaxies possess halos stretching millions of light-years. IC 1101 stood out, not because it was the only one with such a halo, but because its halo was extreme, even by those standards. And this raises a subtle but important point. When we say that IC 1101 would swallow our local group, we are not describing a catastrophic event. We are describing a reclassification of space. The stars of Andromeda would not suddenly collide with stars from the Milky Way. The distances between stars are too vast for that to matter. What changes is the gravitational bookkeeping. Instead of many galaxies orbiting within a group, there would be one dominant galaxy with many internal substructures, the same stars, the same planets, the same empty space, but a different organizational hierarchy imposed by gravity. It is easy to imagine this as a kind of cosmic violence, but in reality, it is closer to slow erosion. Over billions of years, boundaries blur, identities merge. What were once separate systems become parts of a larger whole. IC 1101 represents the end result of that process taken to an extreme. And once you see it this way, another realization begins to form. Our local group is not special because it is large. It is special because we live inside it. From elsewhere in the universe, it would be just one modest collection among many. The idea that a single galaxy could rival it in size is only shocking because we are emotionally invested in our own neighborhood. IC 1101 strips that comfort away. It shows us that the universe is perfectly capable of building structures that make our cosmic home feel small without ever needing to break its own rules. Gravity alone, given enough time and the right environment, is sufficient. Now that we have anchored IC 1101 inches space, not as an abstract number, but as a structure that can be directly compared to everything we know, the next step is unavoidable. We need to confront distance, because IC 1101 is not just vast in size, it is also staggeringly far away. And that distance means that when we observe it, we are not seeing it as it is now, but as it was long before our planet even looked familiar. When we talk about how far away IC 1101 is, we are no longer just talking about space. We are talking about time, distance. At cosmic scales, does something unusual. It stops being a measure of separation and becomes a record of history. IC 1101 is located roughly 1 billion light-years from Earth. That single phrase already contains more information than it seems to. A light-year is not a unit of time, but when you are dealing with objects this distant, distance and time become inseparable. Light travels at a fixed speed, about 300 kilometers per second. Nothing moves faster. Because of that, every time we observe a distant object, we are seeing it as it was when the light began its journey toward us. In the case of IC 1101, the light reaching our telescopes tonight left that galaxy 1 billion years ago. That number is easy to say and difficult to absorb. 1 billion years is not just a long time by human standards. It is long even by geological standards. When that light began traveling toward Earth, the planet you are standing on did not look like the one you know today. At that time, complex life on land did not exist. There were no forests, no insects, no dinosaurs, no mammals. The continents were arranged differently. drifting slowly across the surface of the planet in patterns that would eventually shape the modern world. The oceans were filled primarily with simple life forms. Multicellular organisms existed, but they were primitive and rare. The explosion of complex animal life that would later transform Earth's ecosystems was still hundreds of millions of years away. When astronomers point their telescopes toward IC 1101, they are not seeing a distant galaxy in the present. They are seeing a snapshot from a time when Earth itself was still in an early chapter of its biological story. The galaxy has continued to evolve since then, but that evolution is hidden from us, locked behind a wall of time that light has not yet crossed. This is one of the most counterintuitive aspects of astronomy. We tend to imagine telescopes as tools that let us see far away. In reality, they let us see deep into the past. The deeper we look into space, the further back in time we peer. At 1 billion light years, that past becomes profound. There is an important scientific implication here. The properties we measure for IC 1101, its size, brightness, structure, are properties it had 1 billion years ago. Astronomers can model how galaxies evolve over time and make educated inferences about how IC 1101 may have changed since then. But direct observation always lags behind reality. The universe does not allow us to see the present everywhere at once. This time delay is not a flaw in observation. It is a fundamental feature of the cosmos. It means that the universe presents itself to us as a layered archive, with nearby objects representing the recent past and distant ones representing much earlier epochs. IC 1101 occupies a middle ground in that archive. It is far enough away that time matters, but close enough that its structure can still be studied in detail. The idea that we are seeing a galaxy as it existed 1 billion years ago raises an interesting question. What was IC 1101 like back then? Was it already the colossal structure we infer today? Or was it still in the process of becoming one? Observational evidence suggests that many of the most massive galaxies formed the bulk of their stars early in the universe's history. Studies of stellar populations in giant elliptical galaxies show that their stars are typically old, often more than 10 billion years old. This implies that galaxies like IC 1101 assembled much of their mass long before the light we currently see left them. In other words, even 1 billion years ago, IC 1101 was likely already enormous. This conclusion is supported by observations of distant galaxy clusters. When astronomers look at clusters billions of light years away, they often find massive central galaxies already in place. Their growth may have continued since then, but the foundations were laid early. The universe was more crowded in its youth. Galaxies were closer together. Mergers were more frequent. Growth happened faster. The realization that IC 1101 was already massive when the Earth was still biologically young reinforces how detached cosmic evolution is from human timescales. Entire galactic structures can rise, merge, and settle, while planets quietly develop life that has no awareness of what is happening beyond its sky. There is another subtle consequence of this distance. Because IC 1101 is so far away, its light is faint, not because it is dim intrinsically, but because its light has spread out over an enormous volume of space by the time it reaches us. Each photon that arrives has traveled for 1 billion years, moving through an expanding universe. The longer that journey, the more diluted the signal becomes. This is why studying distant galaxies requires long exposure times and sensitive instruments. It is also why many of the details we take for granted when observing nearby galaxies are difficult or impossible to resolve at such distances. Fine structures blur together. Faint features vanish into noise. What remains is a smoothed, integrated image that must be interpreted carefully. Despite these challenges, astronomers have been able to confirm IC 1101's extreme nature through multiple independent methods, its location within a massive galaxy cluster, the motion of stars within it, the distribution of surrounding hot gas observed in X-rays. All point to a gravitational system of extraordinary scale. Distance complicates observation, but it does not erase the evidence. There is something quietly unsettling about this. A galaxy large enough to dwarf our entire local group exists far beyond our immediate reach. Visible only as a faint smudge through powerful telescopes, it has been there for billions of years, evolving, merging, reshaping itself, while life on Earth took its first tentative steps toward complexity. And yet, the laws governing its behavior are the same ones that govern the atoms in your body. The same gravity that binds IC 1101 together shapes the orbit of the Earth around the Sun. The same physics that drives star formation there once operated in the cloud of gas that became our own solar system. Distance separates us from IC 1101 inches, space and time. But it does not place it in a different universe. It is part of the same cosmic story, unfolding at scales that feel alien only because we are not used to thinking that way. Understanding that story requires more than appreciating size or distance. It requires looking at where IC 1101 lives, not just how far away it is. Because its environment, the company it keeps, is a crucial part of why it became what it is. That environment is not empty space. It is one of the densest regions of the universe. Here is something that sounds almost contradictory. IC 1101 is one of the most massive and luminous galaxies ever observed. Yet, even with a decent telescope, it looks unimpressive. No grand spiral arms. No glowing core visible to the eye. Just a faint, hazy patch that barely stands out from the background darkness. How can something so enormous appear so underwhelming? The answer lies in a concept that does not come naturally to human intuition: surface brightness. When we think about brightness in everyday life, we usually think in terms of total output. A stadium light is brighter than a desk lamp because it produces more light overall. But astronomy forces us to think differently. What matters, just as much as how much light an object produces, is how that light is spread out across the sky. Surface brightness measures how much light arrives from a given area of the sky, not how much light an object emits in total. A galaxy can contain trillions of stars and still appear dim if those stars are spread across an enormous area. IC 1101 is exactly that kind of object. To make this intuitive, imagine two sources of light. One is a laser pointer. The other is a floodlight. The floodlight emits far more total light than the laser, but because it spreads that light over a wide area, no single spot looks particularly intense. The laser, by concentrating its light into a narrow beam, appears dazzlingly bright. IC 1101 is the cosmic equivalent of a floodlight. Its stars are not packed tightly into a compact disk or a bright nucleus. They are dispersed across millions of light years. The result is a galaxy with relatively low surface brightness, even though its total luminosity is staggering. Astronomers quantify this using the magnitude system. IC 1101 has an apparent magnitude of about 14. Under perfect dark sky conditions, the faintest stars visible to the naked eye have magnitudes around 6. That difference may not sound large, but the magnitude scale is logarithmic. Each increase of 5 magnitudes corresponds to a factor of 100 inches brightness. A magnitude 14.7 object is roughly 5,000 times dimmer than what the unaided human eye can detect. This is why IC 1101 is invisible without optical aid. Despite being one of the largest galaxies known, distance contributes to this dimness. But surface brightness is the deeper reason. Even if IC 1101 were closer, its diffuse nature would still make it challenging to observe in detail. This creates a strange disconnect between reality and appearance. How often do we associate size with visibility? Mountains dominate landscapes. Skyscrapers dominate skylines. But on cosmic scales, the largest structures can be the hardest to see. There is a second effect working against us: angular size. Although IC 1101 is millions of light years across, its great distance compresses it into a very small patch of sky. Its angular size is roughly 1 arc-minute across, about 1/30th the apparent diameter of the full moon. If you held a coin at arm's length, it would cover a larger portion of the sky than this galaxy. This combination of low surface brightness and small angular size explains why IC 1101 remained relatively obscure for so long. It was catalogued centuries ago. Yet for most of that time, it was just another faint smudge among thousands. The human eye is particularly poor at detecting extended, low-contrast objects. Our vision evolved to notice edges, movement, and contrast, not faint gradients spread across darkness. That limitation carries over into telescopic observation. Even with magnification, if the light per unit area is too low, the object fades into the background. This is where modern astronomy changes the game. The most detailed images of IC 1101 do not come from someone looking through an eyepiece. They come from long-exposure imaging. Professional telescopes collect photons for minutes or hours, stacking faint signals until structure emerges from the noise. Space-based observatories have been especially important here. The Hubble Space Telescope, free from atmospheric distortion and light pollution, has captured images of IC 1101's inner regions that reveal its smooth elliptical structure. X-ray observatories like Chandra have gone further, mapping the hot gas surrounding the galaxy and the cluster it resides in. That gas, glowing at tens of millions of degrees, outlines the deep gravitational well created by both visible matter and dark matter. These observations are not aesthetic luxuries. They are how astronomers confirm mass, the motion of stars, the temperature of gas, the bending of light through gravitational lensing. All serve as independent checks. When these different lines of evidence agree, confidence grows. One particularly important discovery came from studying the galaxy's stellar halo. Deep imaging has shown that IC 1101 possesses an enormous diffuse halo, extending far beyond its brighter central regions. This halo contains stars stripped from smaller galaxies over billions of years. It is faint, spread thinly across space, and nearly invisible without careful observation. This explains why size estimates for IC 1101 vary so widely in the literature. Some measurements focus only on the bright central regions, yielding diameters of a few 100,000 light-years. Others include the full halo, pushing estimates into the multi-million light-year range. Neither approach is wrong. They are measuring different things. It is similar to asking how big a city is. Do you mean the downtown core, the metropolitan area, the surrounding suburbs that blur into countryside? Galaxies do not come with signposts marking their edges. Their boundaries are conventions, not physical walls. There is another subtle factor at play: cosmological surface brightness dimming. As light travels through an expanding universe, its energy is stretched, reducing its intensity. This effect becomes significant at large distances. For an object a billion light-years away, surface brightness is reduced not just by distance, but by the expansion of space itself. This makes distant, diffuse galaxies particularly hard to detect. It also means that the universe likely contains many large, low-surface brightness structures that we have not yet fully catalogued. IC 1000 may not be unique in its scale, only in our ability to recognize it so far. That realization has driven recent observational campaigns. Surveys like the Sloan Digital Sky Survey first hinted at the population of massive elliptical galaxies in clusters. Newer instruments, including the James Webb Space Telescope and upcoming observatories like the Vera Rubin Observatory, are designed to push deeper, detecting faint extended structures that older surveys missed. What happens when we start seeing those structures clearly? How many other giants are hiding in plain sight? Diluted by distance and darkness, IC 1101 forces us to confront a limitation in how we intuitively judge importance. Brightness catches attention. Compactness feels significant. But the universe does not prioritize what is easy for us to notice. Some of its most extreme objects whisper instead of shout. There is something quietly humbling about that. A galaxy capable of swallowing dozens of others appears, to our eyes, as little more than a blur. Its scale must be inferred, reconstructed through careful measurement rather than direct experience. And yet, once those measurements are made, the implications are unavoidable. If a galaxy this vast can appear so subtle, then the night sky is not just filled with what we see. It is filled with what we have learned how to extract from the darkness. Understanding IC 1101 requires accepting that observation is not passive. It is an act of interpretation, guided by physics, technology, and patience. The faintness of this galaxy is not a failure of detection. It is a lesson in how the universe distributes its grandeur. Size does not guarantee spectacle. Importance does not demand brightness. The cosmos often hides its most extreme achievements behind silence and subtlety. Long before anyone imagined galaxies as vast island universes, IC 1101 was already there, quietly registered as a faint patch of light among many others. Its discovery did not begin with an understanding of scale, distance, or structure. It began with patience, craftsmanship, and a sky far darker than anything most people experience today. The year was 1790. Telescopes were still crude by modern standards, lacking photography, electronics, or digital processing. Astronomers relied entirely on their eyes, their notes, and instruments built by hand. One of the most meticulous observers of that era was William Herschel. Herschel was not originally trained as an astronomer. He began his career as a musician, composing and performing before becoming obsessed with the night sky. What set him apart was not just curiosity, but dedication to building better tools. Rather than purchasing telescopes, Herschel ground his own mirrors by hand, polishing metal for hours, sometimes days. to achieve the precise curvature needed to gather faint starlight. His largest telescope, completed in the late 18th century, featured a mirror nearly 49 inches across and a focal length of 40 feet. For decades, it was the largest telescope in the world. King George III visited it as a spectacle, yet Herschel used it not for display, but for systematic observation. Night after night, Herschel swept the sky, cataloguing thousands of faint objects. Many appeared as small, diffuse smudges, neither sharp like stars nor structured like planets. He labeled them nebulae, from the Latin word for cloud. IC 1101 entered astronomical records during this era. One smudge among many, unremarkable at first glance. At the time, nobody knew what these objects truly were. The prevailing assumption placed all nebulae within the Milky Way. The universe, as far as science was concerned, consisted of one enormous star system and little else beyond it. The idea that each fuzzy patch might be a galaxy comparable to our own lay far beyond accepted thought. Herschel himself suspected something more. He speculated that some nebulae could be island universes, separate stellar systems existing far outside the Milky Way. Evidence to support this idea, however, remained elusive. Telescopes of the era lacked the resolving power needed to distinguish individual stars in distant galaxies. Without that resolution, distance remained guesswork. As a result, IC 1101 sat quietly in catalogues for over a century. Its size, its true nature, its significance remained hidden behind technological limitations. Fast forward to the early 20th century. Astronomy found itself divided by one of the most important scientific debates in its history. On one side stood Harlow Shapley, who argued that spiral nebulae were nearby objects within the Milky Way. On the other stood Heber Curtis, who claimed they were distant galaxies far beyond it. Both presented evidence. Neither could definitively prove their case. The debate culminated in 1920 at the Smithsonian Museum of Natural History, an event now known simply as the Great Debate. No winner was declared that night. The universe remained ambiguous. Resolution came 4 years later through the work of Edwin Hubble, using the 100-inch Hooker telescope at Mount Wilson Observatory. Hubble identified Cepheid variable stars within the Andromeda Nebula. These stars act as cosmic yardsticks. Their pulsation period reveals their intrinsic brightness, allowing distance to be calculated with remarkable precision. Measurements showed Andromeda lay far beyond the Milky Way. The conclusion was unavoidable. Nebulae were galaxies. The universe expanded overnight from one galaxy to billions. Only then did objects like IC 1101 begin to acquire new meaning. What had once been a vague blur suddenly became a candidate for something extraordinary. Improved telescopes, photographic plates, and later, electronic detectors allowed astronomers to revisit old catalogues with fresh understanding. IC 1101 was no longer just a nebula. It was a galaxy, and an unusually large one. Yet, even with this revelation, its true scale took time to emerge. Distance measurements refined through redshift analysis placed IC 1101 roughly 1 billion light-years away. At that distance, apparent size alone could not explain its mass. Something else had to be inferred. Clues came from motion. Stars within IC 1101 moved at velocities far higher than expected for a normal galaxy. Gas in the surrounding cluster glowed intensely in X-rays, indicating deep gravitational wells. gravitational lensing, subtly distorted background galaxies, revealing enormous amounts of unseen mass. Each piece of evidence pointed in the same direction. By the late 20th century, IC 1101 was recognized as the central dominant galaxy of the Abell 2029 cluster, a massive congregation of thousands of galaxies. This position mattered. Central galaxies in clusters experience a very different evolutionary path from isolated ones. They grow by accumulation, absorbing smaller neighbors over billions of years. Detailed studies in the 1,970 seconds and 1,980 seconds, particularly those analyzing galaxy cluster dynamics, revealed how extreme IC 1101 truly was. Measurements of its velocity, dispersion, and diffuse halo suggested a galaxy far larger than anything previously confirmed. One pivotal study in 1979 focused specifically on IC 1101's structure and motion. Results indicated not just an enormous stellar population, but a massive dark matter halo extending far beyond visible light. Subsequent observations with space-based telescopes reinforced this picture. Hubble Space Telescope imaging revealed an unusually large core region, spanning tens of thousands of light-years. X-ray observations from Chandra mapped hot intracluster gas flowing around the galaxy, tracing gravitational contours invisible to optical instruments. Together, these datasets confirmed IC 1101's place among the most massive structures known. Consider the irony embedded in this history. IC 1101 was discovered before humanity even understood what a galaxy was. For more than a century, its true nature remained hidden in plain sight, waiting for theory and technology to catch up. How many other objects share that fate? How many faint smudges in modern surveys will one day be reclassified as something far more extreme than currently imagined? Astronomy advances not just by discovering new objects, but by reinterpreting old ones. IC 1101 stands as a reminder that significance is not always obvious at first glance. Sometimes, importance emerges slowly, revealed layer by layer as tools improve and assumptions fall away. The story of IC 1101 is not just about size, it is about perspective. It shows how human understanding evolves, how entire frameworks can shift, transforming meaningless data points into profound insights. A faint patch sketched by hand in the 18th century eventually became a benchmark for cosmic scale. The galaxy did not change. Human comprehension did. Recognition of IC 1101's enormity forced astronomers to confront a deeper question. If galaxies could grow this large, what mechanisms allowed it? What environments nurtured such growth? Answers to those questions lie not in isolation, but in community. IC 1101 does not exist alone. Its true story unfolds within a crowded, dynamic neighborhood shaped by gravity on the largest scales, and that environment holds the key to understanding how a galaxy becomes a giant. Galaxies do not grow in isolation. Size on the scale of IC 1101 requires more than time and gravity. It requires location. In the cosmic landscape, some regions are sparse and quiet, while others resemble crowded intersections where matter flows, collides, and accumulates. IC 1101 sits in one of the densest environments the universe can offer. Its home is the Abell 2029 galaxy cluster, Galaxy clusters are among the largest structures in the universe that are still held together by gravity, unlike superclusters or cosmic filaments, which stretch across vast distances but are slowly being pulled apart by cosmic expansion. Clusters remain bound. Gravity wins locally, even as space itself continues to grow. Abell 2029 lies roughly 1 billion light-years away and spans somewhere between 6 and 8 million light-years across. Within that volume reside thousands of galaxies, all orbiting a shared center of mass. IC 1101 occupies that center. This position is not symbolic. It is decisive. Clusters function much like cities. Smaller galaxies drift in from surrounding regions, pulled along invisible gravitational currents shaped by dark matter. Once inside the cluster, escape becomes difficult. Over time, the largest and most massive galaxy tends to settle at the center, not by chance, but through a process known as dynamical friction. Dynamical friction sounds abstract, but the idea is simple. As a massive galaxy moves through a sea of smaller galaxies and dark matter, its gravity tugs on surrounding material, creating a wake behind it. Similar to the ripples trailing a boat moving through water, that wake pulls backward on the galaxy, robbing it of momentum. Slower motion causes the galaxy to sink inward toward the cluster's core. Massive objects sink. Smaller ones orbit. Over billions of years, the center becomes a gathering point. IC 1101 did not merely arrive at the center of Abell 2029. It grew there. The cluster itself was catalogued in 1958 by astronomer George Abell as part of his ambitious effort to map galaxy clusters across the sky. Using photographic plates from the Palomar Observatory Sky Survey, Abell identified over 4,000 clusters, classifying them by richness and distance. Abell 2029 stood out early as a particularly massive and relaxed system. Relaxed carries specific meaning in astrophysics. A relaxed cluster has not experienced a recent major collision with another cluster. Its galaxies move in relatively smooth, stable orbits. Hot gas fills the space between galaxies in an even distribution. Such stability allows astronomers to measure mass with greater confidence. Measurements soon revealed something striking. The visible galaxies accounted for only a small fraction of the cluster's total mass. Most of Abell 2029's mass is invisible. X-ray observations provided the first major clue. Instruments like NASA's Chandra X-ray Observatory detected vast amounts of superheated gas permeating the cluster. Temperatures reached tens of millions of degrees. Gas at those temperatures should fly apart unless held in place by an enormous gravitational field. The gravity inferred from visible matter alone was insufficient. Dark matter filled the gap. By analyzing the temperature and distribution of the X-ray emitting gas, astronomers mapped the gravitational potential of the cluster. Results showed a massive dark matter halo extending smoothly toward the center, increasing in density rather than flattening out. This behavior matched predictions from cold dark matter models and contradicted alternative gravity-only theories. Abell 2029 became one of the strongest pieces of evidence supporting dark matter's dominant role in large-scale structure. Estimates place the total mass of the cluster at roughly 100 trillion times the mass of the Sun. Roughly 70 to 90% of that mass exists as dark matter. IC 1101 alone contributes a significant fraction, embedded deep within this invisible scaffold. Dark matter does not glow. It does not emit light. Its presence is inferred through motion, temperature, and lensing. Light from more distant galaxies bends as it passes through the cluster, subtly distorted by gravity. Careful analysis of those distortions reveals where mass resides, even when nothing visible marks its location. Gravitational lensing studies of Abell, 2029, confirm what X-rays suggest. Mass concentrates toward the center, precisely where IC 1101 sits. Such an environment changes how galaxies evolve. In sparse regions, galaxies can retain their gas, forming stars over long periods. In clusters, interactions are frequent. Close passes strip gas. Hot intra-cluster medium prevents cooling. Star formation shuts down. Growth shifts from creation to accumulation. IC 1101 grew by merger, not by birth. Smaller galaxies wandering too close experienced tidal forces strong enough to tear them apart. Stars were stripped and scattered into IC 1101's halo. Dark matter merged seamlessly. Gas, often heated or expelled, failed to form new stars. Over time, individual identities vanished, absorbed into a larger whole. Astronomers sometimes refer to this process as galactic cannibalism. The term sounds dramatic, but the physics is slow and relentless rather than violent. A merger can take hundreds of millions of years. From inside a galaxy, changes would be imperceptible on any human timescale. Evidence of this history remains written in IC 1101's structure. Its enormous diffuse halo contains stars that once belonged to many different galaxies. The smoothness of that halo suggests most major mergers occurred early, giving time for stellar orbits to mix and erase visible traces of collision. Clusters like Abell 2029 also act as laboratories for extreme physics. The interaction between IC 1101 and the surrounding hot gas reveals feedback processes that regulate growth. Jets from the galaxy's central black hole inject energy into the intracluster medium, preventing gas from cooling and falling back onto the galaxy. This feedback loop limits new star formation and stabilizes the system. Without that regulation, IC 1101 might have grown even larger. Consider the scale of what surrounds it. Thousands of galaxies orbit within the cluster, moving at speeds up to 1,400 kilometers per second. Hot gas fills the space between them, outweighing all the stars combined. Dark matter dominates everything, shaping motion and structure from behind the scenes. In everyday terms, imagine standing in the center of a city where every building is moving. Streets are invisible, and gravity itself is the traffic law. That analogy still falls short. The environment of Abell 2029 provided IC 1101 with an endless supply of material during its formative years. Location dictated destiny. Could IC 1101 exist outside a cluster like this? Evidence suggests otherwise. The largest galaxies known almost always occupy central positions within massive clusters. Isolation does not produce giants of this scale. This raises a broader question. If environment plays such a decisive role, then cosmic structure shapes outcome long before individual galaxies have any say in their fate. Growth depends less on internal ambition and more on neighborhood. IC 1101 did not become the largest galaxy because it was special at birth. It became special because it lived at the center of everything that mattered gravitationally. Understanding that environment explains size. But another mystery remains. At the heart of this colossal galaxy lies something even more extreme. something capable of influencing motion across tens of thousands of light years. Something whose mass rivals entire galaxies. That presence waits at the center of IC 1101, shaping everything around it in silence. At the core of IC 1101 lies something so massive that even the galaxy itself must respond to its presence. Not visually dramatic, no swirling vortex visible to the eye, no cosmic roar, just gravity, concentrated beyond anything we encounter elsewhere in the universe. Every large galaxy hosts a supermassive black hole at its center. Ours does too. Sagittarius A, the black hole anchoring the Milky Way, carries a mass of about 4 million suns, by astronomical standards, that already qualifies as extreme. Yet placed beside the central object of IC 1101, it becomes almost insignificant. Estimates suggest the black hole at IC 1101's center contains between 40 and 100 billion solar masses. Even the lower end of that range pushes it into a category shared by only a handful of known objects. Using a conservative middle value of 60 billion solar masses, the scale becomes easier to discuss without losing accuracy. 60 billion suns, compressed into a region of space smaller than the orbit of Pluto. What does a number like that really mean? One way to grasp it is through comparison. If Sagittarius A times were scaled to the mass of a marble, the black hole in IC 1101 would be a boulder the size of a house. Another approach uses orbital mechanics. Stars near the center of IC 1101 move at extraordinary speeds. Far faster than stars near the center of our galaxy, those velocities betray the gravitational grip of something immensely heavy. Direct observation of the black hole itself remains impossible. Black holes emit no light. Evidence comes from indirect signatures, radio emissions, X-rays, jet structures, stellar motion. IC 1101's central black hole is catalogued as a powerful radio source. Designated PKS 1508 plus 059. Radio telescopes detect emissions generated as matter spirals inward, heating and accelerating before crossing the event horizon. Accretion disks form when gas and dust approach a black hole. Friction within these disks raises temperatures to millions of degrees. Radiation spills outward across the electromagnetic spectrum. Under certain conditions, twin jets erupt from the poles, launching particles at near light speed for distances measured in hundreds of thousands of light years. Observations confirm such jets exist in IC 1101. Radio imaging reveals elongated structures extending far beyond the galaxy's visible boundaries. These jets do not just mark activity, they shape the environment. Energy injected into surrounding gas prevents cooling. Without cooling, gas cannot collapse to form new stars. The black hole becomes not just a consumer of matter, but a regulator of growth. Astronomers call this process active galactic nucleus feedback, or AGN feedback. In massive galaxies, this feedback acts like a thermostat. Too much in falling material triggers outflows that heat surrounding gas, cutting off supply. Growth slows. Equilibrium emerges. Why does this matter? Because without such regulation, galaxies could grow uncontrollably, forming stars until gas reserves vanish entirely. Observations suggest AGN feedback explains why the most massive galaxies stop forming stars and become red and dead. IC 1101 exemplifies this outcome. The relationship between a galaxy's mass and its central black hole is not coincidence. Studies reveal a tight correlation between black hole mass and the velocity dispersion of stars in the galactic bulge. Larger galaxies host larger black holes. Growth proceeds together. How does a black hole reach tens of billions of solar masses? Mergers provide the answer. When galaxies merge, their central black holes eventually merge as well. The process takes time. After galaxies coalesce, black holes sink toward the new center through dynamical friction, forming a bound pair. Over millions of years, gravitational interactions with surrounding stars shrink their orbit. At close separation, gravitational waves carry away energy until a single, more massive black hole remains. IC 1101 has experienced many such mergers. Each added mass to the galaxy, each added mass to the black hole. Evidence of this violent history appears in an unexpected place, the galaxy's core. In 2017, analysis of high-resolution Hubble Space Telescope images revealed that IC 1101 possesses the largest depleted core ever measured. The core spans roughly 14,000 light-years. For comparison, the Large Magellanic Cloud, a dwarf galaxy orbiting the Milky Way, measures about that size in its entirety. Depleted cores form during black hole mergers, as two supermassive black holes spiral inward. Surrounding stars interact gravitationally, receiving energy boosts that fling them outward. Astronomers call this process gravitational slingshot ejection. Stars, once crowded near the center, are scattered into the outer halo, or even expelled into intergalactic space. Repeated mergers amplify the effect. Over billions of years, the core becomes vast and sparsely populated. Estimates suggest IC 1101's core has lost roughly 490 billion solar masses worth of stars. That amount exceeds the total stellar mass of many entire galaxies. What kind of system ejects more mass than most galaxies contain? One dominated by extreme gravity. Such a core provides strong evidence for multiple black hole mergers. Each event hollowed the center further, leaving behind a gravitational signature too large to ignore. No other known galaxy exhibits a core of comparable scale. The event horizon of a 60 billion solar mass black hole would itself be enormous. Calculations place its radius near 170 billion miles. Earth's orbit around the Sun would fit inside that boundary nearly 900 times over. Imagining such an object placed at the center of our solar system strains intuition. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, all would lie well within the point of no return. Yet scale does not imply violence at a distance. From far enough away, gravity behaves predictably. Stars orbit IC 1101's black hole peacefully, unless they venture too close. The monster dominates quietly. Why do such black holes exist at all? Current theories suggest early formation. Seed black holes may have formed from direct collapse of massive gas clouds in the early universe, or from the remnants of the first generation of stars. Rapid growth followed during periods when gas was abundant and mergers frequent. By the time the universe matured, the largest black holes had already claimed their place. IC 1101's black hole likely grew quickly in the cluster's early history. Later growth slowed as gas supplies dwindled and feedback stabilized the environment. Today, the black hole accretes at a modest rate relative to its size, roughly equivalent to a few hundred solar masses per year. Impressive by human standards, insignificant compared to its total mass. Such an object will persist for an almost unimaginable duration. Black holes evaporate through Hawking radiation. But for one this massive, the timescale exceeds 10 to the power of 100 years, long after stars fade and galaxies darken. This black hole will remain at the heart of IC 1101. Gravity has reached its most concentrated expression. Understanding this central monster reframes the galaxy itself. IC 1101 is not merely large, it is structured around an engine capable of reshaping its surroundings on scales rivaling galaxies. Size, environment, history, regulation, each thread converges at the center. Yet one final piece remains to be understood. If IC 1101 contains so many stars, spreads across millions of light years, and hosts one of the largest black holes known, why does it look so quiet? The answer lies not in violence, but in age, and that leads directly to what IC 1101 has become today. At first glance, IC 1101 seems like the ultimate symbol of abundance, a structure spanning millions of light years, a gravitational halo large enough to engulf entire groups of galaxies, an estimated stellar population approaching 100 trillion stars. With numbers like that, one might expect chaos, explosive starbirth, brilliant blue regions blazing across its disk. Instead, telescopes reveal something unexpected. Stillness. The light from IC 1101 carries a warm, yellow-red tone, not the bright blue glow associated with young, massive stars. Astronomers recognize this color immediately. It signals age, not decay in the human sense, but maturity on cosmic timescales. Most stars in IC 1101 formed billions of years ago. To understand why this matters, consider how stars are born. Star formation requires cold gas, primarily hydrogen dense enough to collapse under gravity. Where gas flows freely and cools efficiently, new stars ignite. Spiral galaxies excel at this. Their rotating disks compress gas along spiral arms, triggering star formation again and again. IC 1101 lacks such conditions. Observations across infrared and optical wavelengths show little cold gas. The reservoirs that once fueled starbirth have either been consumed, heated beyond usefulness, or expelled entirely. Without raw material, even gravity cannot create new stars. Astronomers refer to galaxies like this as red and dead. The phrase sounds dramatic, yet describes a slow, quiet transition. Star formation fades. Existing stars age. The galaxy glows softly as its population shifts toward longer-lived, cooler stars. Red dwarf stars dominate. Small, efficient, and incredibly patient. Many will shine for trillions of years, far longer than the universe's current age. Sun-like stars continue burning, but no replacements follow once they exhaust their fuel. How did IC 1101 lose its gas? Mergers again provide the explanation. Every collision between galaxies disrupts gas clouds. Shocks compress some regions, triggering short-lived bursts of star formation. At the same time, violent interactions heat gas and fling large fractions outward. In cluster environments, hot intra-cluster gas strips remaining material through a process known as ram pressure stripping. Imagine riding a bicycle through thick air. The faster you go, the more resistance you feel. Galaxies moving through dense cluster gas experience a similar effect. Their own gas is pushed backward, peeled away, and left behind. IC 1101 101 sits at the center of Abell 2029, surrounded by gas heated to tens of millions of degrees. X-ray observations from the Chandra Observatory reveal a smooth, spherical cloud filling the cluster. Cold gas entering this environment rarely survives long enough to form stars. Add AGN feedback from the central black hole, and the outcome becomes inevitable. Energy injected into surrounding space prevents cooling. The star-forming cycle shuts down. Despite this quiet present, the scale of IC 1101 stellar population remains staggering. Estimates place the number of stars near 100 trillion, roughly 300 times the Milky Way's total. Counting one star per second would take over 3 million years. Human civilization would rise and fall many times before finishing the task. Each of those stars represents a nuclear furnace. Many host planets. Studies of exoplanet frequency suggest most stars possess at least one planet. If IC 1101 follows the same trend, the galaxy could contain hundreds of trillions of worlds, rocky planets, gas giants, icy bodies, moons orbiting moons. Could life exist among them? Statistics alone suggest possibility. Chemistry does not care about scale. Carbon, water, energy gradients. These ingredients are common. Given enough trials, some combinations succeed. Whether intelligence emerges remains unknown, yet distance imposes silence. IC 1101 lies roughly 1 billion light-years away. Any signal sent today would arrive long after Earth itself changes beyond recognition. Observation works only one way. Looking at IC 1101 means looking backward in time. The light reaching telescopes tonight left the galaxy 1 billion years ago. At that moment, Earth hosted only primitive multicellular life. Forests had not formed. Fish did not swim. Dinosaurs remained far in the future. Civilizations capable of building telescopes existed nowhere. This time delay carries philosophical weight. IC 1101 appears frozen, not because nothing happens there, but because information travels slowly. The galaxy could already be dimmer or slightly different today. We cannot know yet. Astronomers reconstruct its history using population studies. Spectral analysis reveals star ages, metallicity, and formation epochs. Results consistently indicate early, rapid star formation followed by long quiescence. IC 1101 formed its stars quickly, efficiently, and early. Growth peaked when the universe itself was younger and richer in cold gas. Later epochs brought mergers without renewal. Contrast this with the Milky Way. Star formation continues at a modest rate, 1 to 2 solar masses per year. Spiral structure persists. Gas flows inward from the halo. IC 1101 lacks such circulation. Different environments produce different outcomes. A useful analogy comes from ecology. Consider a forest growing on fertile land versus one in a harsh desert. Both may reach impressive size, but only one sustains continual renewal. IC 1101 resembles an ancient forest whose growth spurt ended long ago. Massive trunks remain. New saplings rarely appear. This does not diminish its importance. On the contrary, galaxies like IC 1101 represent an endpoint. They show where cosmic evolution leads under certain conditions. Dense environments, frequent mergers, powerful central engines. Understanding these systems informs broader cosmology. Why do star-forming galaxies dominate some regions while others fade early? How do black holes regulate growth? Why does structure formation stall at extreme scales? IC 1101 provides a natural laboratory for these questions. Even in stillness, information flows. The galaxy's smooth stellar halo preserves evidence of ancient mergers. Its depleted core records black hole interactions. Its color encodes billions of years of stellar aging. Nothing here is random. Quiet does not mean simple. And while IC 1101 may no longer blaze with newborn stars, its future stretches almost beyond imagination. Trillions of years of gradual fading await, long after spiral galaxies exhaust their fuel. Red dwarfs here will continue glowing faintly. Eventually, darkness wins everywhere. But before that happens, IC 1101 stands as a monument to cosmic excess, proof that nature builds not just big, but overwhelmingly so. Next comes a question that naturally follows. If this galaxy is so enormous, so dominant, so extreme, why did it form here, at the heart of a cluster, and not elsewhere? That question leads us outward, beyond the galaxy itself, into its larger cosmic neighborhood. No galaxy grows in isolation. Even the largest ones are shaped, guided, and ultimately limited by the environment they inhabit. Xantun is no exception. Its extraordinary size begins to make sense only when you stop looking at the galaxy itself and zoom out to the structure surrounding it. IC 1101 sits at the very center of a massive galaxy cluster known as Abell 2029. Galaxy clusters are among the largest gravitationally bound structures in the universe. Thousands of galaxies orbit within them, not unlike bees moving around a hive, each following paths dictated by gravity rather than intention. Unlike superclusters or cosmic filaments, which are slowly pulled apart by cosmic expansion, galaxy clusters remain intact. Their combined gravity is strong enough to hold them together for billions of years. Abell 2029 lies roughly 1 billion light-years from Earth. In the general direction of the Virgo constellation, its diameter spans several million light-years, comparable to the full extent of IC 1101 itself. Within that volume, thousands of galaxies move at speeds approaching 1,000 to 100 kilometers per second. At the center of all this motion sits IC 1101. This placement is not coincidence. Over time, gravity sorts structures by mass. Heavier objects lose orbital energy more efficiently through a process called dynamical friction. As massive galaxies move through a sea of smaller galaxies and dark matter, they create a gravitational wake behind them. Much like a boat moving through water, that wake pulls backward, slowing the galaxy down. Slower objects sink over billions of years. The most massive galaxy in a cluster inevitably drifts toward the center. Once there, it becomes a gravitational trap. Smaller galaxies passing nearby lose energy, spiral inward, and are eventually absorbed. Growth accelerates simply because mass attracts more mass. IC 1101 represents the extreme outcome of this process. Observations across multiple wavelengths confirm this picture. Optical surveys map the distribution of galaxies. Radio observations trace jets from the central black hole. X-ray telescopes reveal something even more important: hot, intracluster gas filling the entire cluster. NASA's Chandra X-ray Observatory provided some of the most detailed images of Abell 2029. What it saw was not turbulence or recent chaos, but smoothness. The gas forms a nearly spherical halo centered precisely on IC 1101. Temperatures reach tens of millions of degrees. Gas, that hot, does not cool easily. This matters because cooling gas fuels star formation and galactic growth. In Abell 2029, most of the gas remains suspended, locked in place by gravity, unable to condense. The cluster appears dynamically relaxed, meaning no major cluster-scale collisions have occurred recently. That calm tells astronomers something crucial. IC 1101 did most of its growing early, when the universe was denser and mergers more frequent. Recent times have been quieter, yet the most dominant ingredient of this environment remains invisible. Dark matter. Galaxies alone do not account for the cluster's mass, nor does the hot gas. Measurements of galaxy velocities show that something unseen provides most of the gravitational pull. Without it, galaxies would fly apart. Gravitational lensing studies confirm this. Light from more distant galaxies bends as it passes through Abell 2029, revealing a massive dark matter halo enveloping the entire cluster. Estimates suggest that dark matter accounts for roughly 80 to 90% of the cluster's total mass. Think of dark matter as the scaffolding of the universe. Ordinary matter stars, planets, gas hangs from it like decorations. Remove the scaffolding, and nothing holds together. In Abell 2029, that scaffold deepens toward the center. Dark matter density rises smoothly all the way into IC 1101 itself. This matches predictions from cold dark matter models and provides one of the strongest confirmations of our standard cosmological framework. Why does this matter for IC 1101 size? Because dark matter defines the potential well. The deeper the well, the more material can be captured and retained. IC 1101 sits at the lowest point of one of the deepest wells in the local universe. Escaping requires enormous energy. Most galaxies never manage it. Imagine dropping pebbles into a deep pit. Some bounce, some roll away. Enough fall in, and the pit fills. IC 1101 is that pit on a cosmic scale. The cluster environment also limits future growth. Although many galaxies remain in Abell 2029, the supply is finite. As IC 1101 consumes nearby systems, fewer remain. Expansion of the universe further isolates clusters from one another, cutting off fresh infall. Growth slows. Dominance stabilizes. This raises a subtle but important point. Bigger does not mean eternal. IC 1101 represents a peak, not an endless trajectory. Its environment enabled rapid growth early on, then imposed a ceiling. Could an even larger galaxy exist elsewhere? Possibly. Astronomers continue to search for extreme systems in denser or younger clusters, especially with new instruments like the James Webb Space Telescope and upcoming surveys from the Vera Rubin Observatory. Yet physics imposes limits. Gas supply, merger rates, and dark matter distribution all constrain size. IC 1101 approaches those limits. Seen this way, the galaxy becomes more than a record holder. It becomes a boundary case, a test of how large coherent structures can grow before the universe itself says no more. Understanding that boundary helps define cosmic architecture. And once that architecture is understood, attention naturally shifts inward again. Back toward the core, toward the single object powerful enough to influence the entire galaxy and beyond. At the heart of IC 1101 lies something that scales even more extremely than the galaxy itself. A black hole so massive that its gravity reshapes stars, gas, and space around it. At the center of IC 1101 lies an object so extreme that even within a galaxy of 100 trillion stars, it still dominates everything around it. A supermassive black hole, not merely large by familiar standards, but among the most massive ever measured. The black hole at the heart of IC 1101 is estimated to contain somewhere between 40 and 100 billion times the mass of our Sun. Even the lower end of that range places it far beyond what most galaxies host. For comparison, the black hole at the center of the Milky Way, Sagittarius A, contains about 4 million solar masses. Impressive. Certainly, yet next to IC 1101's black hole, it barely registers. Picture a marble beside a mountain. Mass determines gravity, and gravity shapes motion. In the inner regions of IC 1101, stars do not orbit gently as they do in spiral galaxies. Their paths are fast, chaotic, and tightly bound. Measurements of stellar velocity dispersion show stars whipping around the center at enormous speeds, responding to a gravitational pull that overwhelms everything else nearby. This black hole is catalogued as PKS 1508+059. A strong radio source. Radio emissions tell astronomers something important. They signal active accretion, matter falling inward, heating up, releasing energy. When gas approaches a black hole, it does not plunge straight in. Conservation of angular momentum forces it into a rotating disk. Friction within that disk heats the material to millions of degrees. Radiation spills outward across the electromagnetic spectrum. From radio waves to X-rays, jets emerge along the poles. In IC 1101, those jets extend far beyond the visible galaxy. Injecting energy into the surrounding cluster, they interact with hot intracluster gas, stirring it, heating it, preventing it from cooling. This process, known as active galactic nucleus feedback, plays a decisive role in shaping the galaxy's fate. Why does this matter? Because cooling gas forms stars. Heated gas does not. The black hole acts as a regulator. Feed it too much material, and it responds violently, cutting off its own supply. A cosmic thermostat. Growth triggers restraint. This feedback helps explain why IC 1101 stopped forming stars long ago. Even if some gas drifted inward, energy from the black hole would have reheated it before collapse could occur. Starbirth stalls. The galaxy settles into long-term quiet. The size of the black hole also leaves an imprint on the galaxy's structure. IC 1101 possesses the largest galactic core ever measured. Observations using the Hubble Space Telescope indicate a core radius of roughly 4 doi kiloparsecs, about 14,000 light-years. That distance rivals the diameter of entire dwarf galaxies. How does a core grow so large? The answer lies in black hole mergers. When galaxies collide, their central black holes eventually spiral toward one another. As they do, they interact gravitationally with nearby stars. Some stars gain energy and are flung outward, ejected from the core region entirely through a process known as gravitational slingshot. Each merger clears out the center a little more. Over billions of years and many mergers, the effect accumulates. IC 1101's core is depleted. Estimates suggest that nearly 500 billion solar masses worth of stars have been displaced from the central region. 500 billion suns scattered. Those stars now populate the vast diffuse halo surrounding the galaxy, contributing to its enormous size. The smoothness of that halo indicates ancient activity. Time has erased sharp features. Orbits have mixed. Memory has faded. Yet the physics remains readable. This black hole did not appear fully formed. It grew alongside the galaxy, feeding on gas early, then on other black holes during mergers. Every absorbed galaxy contributed not only stars and dark matter, but another central black hole. Mass begets mass. At its current accretion rate, estimated at a few hundred solar masses per year, growth is slow. At this pace, adding even 1% to its mass would take tens of millions of years. The most rapid growth happened long ago, when cold gas was abundant and collisions frequent. Even now, its influence persists. The event horizon of a black hole this massive would extend hundreds of billions of miles. Place it where the sun is, and its boundary would swallow the orbits of every planet, including Pluto, many times over. Nothing familiar would remain. Is this black hole unusual or inevitable? Astronomers find a strong correlation between galaxy mass and black hole mass. Larger galaxies host larger black holes. The relationship holds across many orders of magnitude. IC 1101 sits at the extreme end, but it follows the same trend. Push galactic growth far enough, and gravity demands a central monster. In this sense, the black hole is not an anomaly. It is the natural consequence of IC 1101's history, a record of everything the galaxy has consumed. And yet, for all its power, even this black hole has limits. Over unimaginable timescales, quantum effects slowly erode it through Hawking radiation. The process is absurdly slow. A black hole of this mass would take around 10 to the power of 100 years to evaporate. Numbers so large they lose intuitive meaning. Still, the implication remains. Nothing is truly permanent. Not stars, not galaxies, not even the largest black holes ever formed. IC 1101 contains one of the deepest gravitational wells the universe has produced. Its black hole anchors the galaxy, regulates its growth, sculpts its structure, and marks the endpoint of violent assembly. Understanding that core completes the picture. A galaxy shaped by mergers, a cluster shaped by dark matter, a center shaped by gravity pushed to its limit. From here, only one direction remains to explore. Forward, not inward or outward, but ahead in time, toward the long future waiting for a galaxy that has already lived most of its active life. For most of its existence, IC 1101 has been defined by growth. Galaxies falling inward, stars added layer by layer, a central black hole swelling with every merger. Yet growth is not the natural end state of the universe. Expansion, dilution, and exhaustion eventually take over. Even for the largest structures ever assembled, IC 1101 has already crossed that threshold. What remains now is not evolution driven by violence, but change governed by time. Star formation within IC 1101 has effectively ceased. The cold hydrogen needed to ignite new stars is gone, either consumed long ago or heated beyond usefulness by mergers and energetic feedback from the central black hole. Without replenishment, the galaxy cannot renew itself. Existing stars continue their lives uninterrupted, but no younger generation rises behind them. The stellar population ages as a whole, slowly shifting toward dimmer and longer-lived stars. Over the next billions of years, the most massive remaining stars will disappear first. These stars burn through their fuel quickly, swelling into red giants before collapsing into neutron stars or black holes. Sun-like stars follow on longer timescales, living for around 10 billion years before shedding their outer layers and leaving behind white dwarfs. Each transition releases energy, but on the scale of IC 1101, these events blur into a steady background rather than dramatic milestones. Eventually, red dwarf stars dominate almost completely. Small, efficient, and extraordinarily patient. These stars can burn for trillions of years. For an unimaginably long time, IC 1101 will remain faintly illuminated by their glow, a galaxy still visible but slowly dimming. From afar, it will appear increasingly red, increasingly quiet, increasingly ancient. Nothing catastrophic happens. No final explosion announces the end. Change arrives as absence rather than destruction. Gravitational structure persists long after light fades. Stars continue orbiting the galactic center. The dark matter halo remains intact, binding everything together even as luminous matter grows scarce. White dwarfs cool gradually. Neutron stars spin down. Black holes drift silently through the galaxy. The supermassive black hole at the center outlives almost everything else, its influence undiminished, even as the galaxy around it grows darker, over timescales far exceeding the current age of the universe. The internal dynamics slow further. Stellar encounters become rarer. Energy exchanges flatten out. The galaxy approaches a state astronomers describe as dynamically relaxed, where large-scale change effectively stops. IC 1101 becomes a fossil of structure rather than an engine of transformation, preserving the outcome of billions of years of cosmic assembly. Eventually, even starlight fades almost entirely. White dwarfs cool toward near invisibility. Red dwarfs exhaust their fuel. What remains is a galaxy defined more by mass than by light. A vast gravitational system drifting through an expanding universe. IC 1101 does not disappear. It simply becomes harder and harder to notice, its presence inferred through gravity rather than illumination. In this future, IC 1101 is no longer remarkable because of what it does, but because of what it represents. It is a record of how large structures form, grow, and settle, a reminder that even the most extreme examples of cosmic abundance eventually yield to time. Size delays the end, but it does not prevent it. IC 1101 challenges intuition, not because it is merely large, but because it forces a rethinking of scale itself. A single galaxy containing 100 trillion stars stretches human imagination beyond comfortable limits. Yet despite that immensity, existence within it would not feel dramatically different from life inside a much smaller galaxy. A planet still orbits one star. Days still pass. Life, if it exists, unfolds locally, indifferent to the size of the structure enclosing it. This disconnect between cosmic scale and lived experience is one of the universe's quiet paradoxes. From within, even the largest galaxy feels ordinary. Only distance reveals excess. Only measurement exposes extremes. IC 1101 reminds us that significance depends on perspective. What seems overwhelming from afar becomes background up close. At the same time, knowledge changes perception. Knowing that such structures exist reshapes how we understand our place in the universe. The Milky Way, once imagined as the entirety of existence, becomes one example among countless others, not special in size, not central in location, simply one outcome among many governed by the same physical rules. IC 1101 demonstrates how far those rules can be pushed. Gravity gathers matter. Dark matter shapes scaffolding. Mergers amplify mass. Black holes regulate growth. Nothing exotic is required. No new physics needs to be invoked. Extreme outcomes emerge naturally when ordinary processes operate long enough under the right conditions. That realization carries a subtle message. The universe does not aim for balance or moderation. It explores possibilities, given time and material. It builds structures that verge on the incomprehensible. IC 1101 is not an exception to cosmic order. It is an expression of it. There is also humility in recognizing limits. Even this galaxy, among the largest known, exists within boundaries imposed by expansion, resource availability, and time. Growth halts, energy dissipates, complexity gives way to simplicity. Nothing escapes entropy forever. Not stars, not galaxies, not even black holes. Yet meaning does not vanish with impermanence. Understanding IC 1101 adds depth rather than despair. It places human existence within a broader continuum, neither central nor irrelevant. We are brief, but we are capable of comprehension. Atoms assembled by ancient stars now observe structures billions of light years away and reconstruct their histories. That capacity alone is remarkable. IC 1101 will never know it has been measured. Its stars shine without awareness. Its black hole consumes without intention. Meaning arises not from the object, but from the act of understanding. In studying such galaxies, the universe becomes aware of itself through us, if only for a moment. Perhaps that is the quiet resolution of this journey. Not awe for size alone, but appreciation for context. IC 1101 shows what the universe can build. Our existence shows what it can reflect upon. Both are products of the same laws, unfolding at different scales. Long after our species is gone, IC 1101 will continue drifting through space, dimmer than before, quieter than ever. Long after that, it too will fade. But for now, its light reaches us across 1 billion years, carrying a message without words. The universe is larger, older, and more patient than intuition suggests. And still, it is knowable. That is enough.